Good morning and good afternoon, good evening from wherever you're joining us from. My name is Dave Cadu, and I am honored to be the CEO and Director of IWCS. Please note that we are, as an attendee, you are part of a larger audience. And during the presentation, all participants will remain in listen-only mode. And also, as a reminder, this event is being recorded for rebroadcast. We encourage you to submit your written questions at any time during the presentation using the chat panel on the right of your screen. After typing your questions in space at the bottom, hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. Our IWCS webinar series event today is hosted by our Cable and Connectivity Industry Forum. Hopefully, many of you were with us a few weeks ago. It was a very successful event, and we certainly hope to be with us again next year. So today, we welcome Michael Heinz, who is a Process Development Manager for Global Materials with Corning Optical Communications. He's located in Berlin, Germany, and Michael did present this paper. It was paper 6-5 a few weeks ago, and you will be able to access that on our archives within a few short weeks on our website. But if you are part of the event, then you can go into the content library and get his paper if you want to follow along. Michael will be presenting his paper on cable friction, influence of cable and duct materials in extended testing. Michael is leading the process development team of the Global Materials Group at the Corning Technology Center in Berlin. After working as a development engineer for copper cables for 3 years, he joined Corning in 2014 as a development engineer with focus on material science. The major scope of his work is the development of flame-retardant fiber optic cables, materials and processing methodology. Special focus lies on flame-retardant cables and halogen-free flame-retardant compound development and testing. Michael earned a degree in materials science and engineering at the University of Beirut. He has over 13 years of experience in polymer materials development, processing, and testing, including 10 years in the wire and cable industry. So with that, Michael, we thank you for being with us again today, and we look forward to your presentation. If you want to take it away.
Hello, everyone. Can you see my screen already?
Yes, looks good.
Okay, perfect. So first of all, thank you very much for giving me the opportunity to share this paper and this content, and also the lot of work that we did to investigate all the different effects on cable friction, especially as you already mentioned, different kind of cable materials, duct materials, and a certain amount of extended testing. First of all, I want to just quickly go through the state of the art and also the reason why we did the work, and giving you some kind of overview about the different materials and methodology that we applied, especially when we talk about friction testing, and also the different cable materials and duct materials, to avoid that it gets a bit too confusing overall, because we tried several hundreds of combinations of the tests, and then directly to the results, where we want to understand the influence of the coefficient of friction on the one hand by the sample testing method, but also the sheathing materials, the lubricants, the additives that we used, and also the duct materials. Overall, first of all, the big question to clarify is, why do we want to understand the coefficient of friction of cables? This is mainly of interest in the blowing and pulling and pushing methodology by installing a cable into pre-installed ducts. So for example, the blowing technology, you can see that here, where a cable, you see them still on the drum, is pushed into a duct and is flowing in there on an air stream. So this is the so-called blowing technology. And therefore, you can install several kilometers of cable into pre-installed ducts, which gives you a very high flexibility in regard of sample exchange, but also the installation of cables maybe a bit later. So you have some opportunity there. To do that, you need a blowing device, which consists of a caterpillar and a machine that controls the cable installation speed, but also the compressed air to get the right ratio of the parameters. Just looking at this in a schematic overview, you can see that the caterpillar on the left pushes the cable into a blowing head where the cable is then confronted with the compressed air, and the cable is pushed into the duct and is flowing there on a certain airstream. Up from a certain length of cable that is installed in the duct, a drag force is created of the compressed air and the cable is pulled in. But until then, you need to push with a certain force into the duct. Of course, things don't always go well. So therefore, we need to understand that when we push the cable into the duct, we are faced with friction of the cable and the duct. And so if the cable friction exceeds a certain value, we have two failure modes, which are identified as, on the one hand, buckling of the cable in the duct, which can cause attenuation increase on fiber optic cables. And on the other hand, kinking, which is, you can see the second option, which is by far more critical of damaging the cable. In the real installation world, it looks like this. So we have the buckling here on the bottom right, where the cable then stops and cannot be pushed further. So in the end, to avoid this kind of cable damage and breaks, we need to understand how we can reduce the coefficient of friction and what in general affects the whole blowing performance. So in advance for this work that I'm showing, I've investigated, of course, literature, and I've identified more than 15 laboratory scale test methods to determine coefficient of friction. So we're not talking about a universal test method, and especially not for cable and cable installation. If we then move to different material combinations of different types of material, things get even more complicated. So in the end, I ended up with 5 different databases for coefficient of friction values of material in contact with HDPE, because HDPE is the material that the ducts are made of. So I've looked for these values with the minimum and maximum values that these databases gave me. So we started with HDPE with itself, and based on the database, you can either use the value of 0.1 to the value of 0.45, which I would say is a pretty decent difference. If we talk about polyamides, which are expected to have a reduced friction, so at least that's what the suppliers tell us, we talk about minimum values of 0.13, but even max values of 0.7. Steel seems to be a bit better in regard of the scattering or the deviation. But one funny part was, as I was investigating some lubricated steel with HDPE, it seems that the friction is even higher. And then, of course, for me as a technical person, the very first question coming up with just like, okay, lubricated with what and how much of lubricant? So actually, I need to say that all my literature research just came up with more questions than answers. So I had a very unclear picture. And even without considering different material mixtures, like for example, low smoke, zero halogen compounds, where we have a mixture of different polymers and properties. So therefore, we used a test method in IEC TR 62470, which is the friction of a cable in a duct. So this is not a standard, this is rather a recommendation of a test method. So we applied a duct, which is wrapped around a mandrel, in our case, a diameter of 430 millimeters. And you have a load at the end, which is F0 here, and which ensures that the cable is always in touch with the inner part of the duct. And the other end is fixed to a tensile tester, and we have a measured force, which is in the end, we pull the whole thing 300 millimeters, and we average the force between 50 and 300, so that we get rid of the initial friction force that is, of course, higher due to the stick slip effect. The coefficient of friction is then calculated by this equation here, and then can be directly compared. So, but the thing is, the standard is only a recommendation. It does neither give us instruction about how many samples should we test, or how often should we exchange the samples, or even the ducts. So therefore, we use different cables to investigate this, starting with micro cables with a small outer diameter. They mainly differ in the jacket material and in the outer diameter. So we talk about HDPE on the left hand with microcable 1, and halogen-free flame retardant compounds like low smoke zero halogen is an indoor cable, because both of them are now installed by blowing, and so therefore it is of interest of both. Both have 12 fibers, and the diameter differs from 2.5 to 3. Of course, now you could say, okay, the diameter is a very important part, so because of this free space in the duct. So that's why we also moved to a bit larger cable, which is a 96 fiber mini extend cable. And we produced 5 different cables with the same outer diameter, the same cable core, everything the same, just with different jacket materials. So MX1 has a jacket material of high density polyethylene. MX3 has a polyamide 12, and MX4 is a low smoke zero halogen cable compound. We also incorporated 2 different kind of polymeric additives to further reduce the coefficient of friction, to understand how we can affect the coefficient of friction by an addition of a polymeric additive, which is an ultra high molecular weight siloxane. So this is only miscible with a polyethylene base. So therefore we added this in MX2 to the HDPE, and in MX5 to the low smoke zero halogen compound, because this one is based on EVA LLDPE compounds. Of course, we do not only vary the cables, we also varied the ducts. So we started with ducts for microcables. The duct name is always the inner diameter of the free space. That means a D4 is an inner diameter of 4 millimeter and is made of polyethylene. We also tried a D4FR, which is a flame retardant polyethylene, because this is mainly used for indoor installation in buildings when we talk about these microcables. The loose tube cables that we used, these mini extend cables, do not need to be flame retardant, because we talk about outdoor cables. So therefore, we varied 2 different duct sizes, 8 and 10 millimeter. Furthermore, to be more realistic, we also performed all the tests dry and with a blowing lubricant applied on the sample to understand also the effect of the lubricant. So first of all, before we started, we investigated the sample test method, as I already mentioned, that it is not yet really clear about how often to exchange or not. So I will going to show you a lot of graphs now in the next slides, and you will always say on the y-axis the coefficient of friction, and on the x-axis the number of tests. Because of a simple reason, we just repeated the tests after another, also to investigate how does the sample be affected over a long-term blowing, because we do not only talk about 1 meter blowing, we want to blow several kilometers. So we want to have some long-term effects. So we have the micro cables here, which is the MC1, the blue curve with HDPE, and the MC2 in the red curve with the low smoke zero halogen cable compound. We repeated the tests 10 times, and we see that the HDPE exhibits less friction than the low smoke zero halogen compound. We expected that because the LSZH compound is a bit more rubbery, it is more flexible, and is not as hard on the HDPE. But for both cables, we see signs of abrasion because the friction increases with every test run. And so we have a slight increase in friction over time. If we now react on that and exchange the cable every time, but leave the duct the same, we did this to understand where does the friction occur. And so you can see here on the dotted lines, this is new cable, same duct after every sample. So we talk here about 10 different cables tested after another. And with a fresh cable on each test, the performance, the difference in between HDPE and LSZH stays relatively comparable. But the friction decreases over time, which is a sign that the abrasion that we observed occurs at the cable and not at the duct. Now moving forward on the different types of sheathing materials, where we of course stayed with 10 tests repeating the same specimen after another to investigate the long-term stability. And we have the results here with HDPE in blue, the polyamide in red, and the low smoke zero halogen in black. The HDPE exhibits a slow increase of friction over time, what we just saw. This cannot be seen for the polyamide, and the values of the polyamide are lower than HDPE. So we have a very stable performance at lower force. The low smoke zero halogen actually was barely movable. It was very difficult to measure, and we see a slight increase of friction over time, but we have noticed that this was at the upper detection limit because of the big cable outer diameter. Nevertheless, we also then tried this to apply a lubricant and tested the same cables with the same 10 repeats. You can see them here. So the results are already added in the graph on the dotted lines. The application of lubricant decreased the friction values significantly for all materials. You can barely differentiate the blue and the red dotted lines because they're just so close. So they're very good values, even below 0.1, which is pretty good. For all the cables, all the signs of abrasion are gone. The low smoke zero halogen compound still shows a higher friction values, but actually now it's on a level of dry polyamide, which is already pretty good. So I would say the addition of lubricant has very positive effects. We also tried to modify and influence the coefficient of friction not only by the lubricant, but also by the polymeric additive, which I already said we added this into HDPE and LSZH. So the graph changes a little bit to incorporate all the data. The coefficient of friction values here are the average values now of all 10 tests. So that means if we have increased friction and abrasion, this is already added into these values. So the red curves here are the dry tests and the blue in lubricant. So we also used ultra high molecular weight siloxane additive and a lubricant to double check on that one. What can be seen here that from MX2, the HDPE with additive and the values for polyamide are comparable. So even in a dry test, no lubricant, the HDPE with the additive plays in the same league like a polyamide. Furthermore, on the LSZH material, we see a drop in coefficient of friction by 78%, which is, I would say, outstanding there, on the same level like a HDPE with additive. In general, also by admixing the polymeric additive, all signs of abrasion were gone. But I need to say that we did not see any benefit in combining lubricant and the additive. So either you take the one or the other approach and you're good to go. Of course, we did not only investigate the cable materials, but also investigate the different duct materials. As I already mentioned, we have normal PE ducts and flame-retardant PE ducts. So the flame-retardant HDPE duct is expected to cause higher friction due to the incorporated flame retardant additives. And so you can see it here. It is again the microcable with HDPE in blue and the LSZH microcable in a standard polyethylene duct. So the abrasion effects, you already know them. They are observable on both cables. And now testing that in the dotted lines in the flame retardant PE duct, you can see that the LSZH cable is affected by higher friction in the flame retardant duct. But the much harder HDPE sheath on microcable 1 in blue does not show a difference either if it's a polyethylene duct or a flame retardant polyethylene duct. Of course, we wanted to understand, does lubricant also help here? And what effect does it have? So we again started testing the duct materials, different duct materials with lubricants. So again, the dotted lines are the flame retardant ducts. The solid lines are the ducts with lubricant, but the standard PE ducts. In general, all the coefficient of friction values decreased from the slide before a lot, which on the one hand, on the pure HDPE is 74% coefficient of friction reduction by lubricant, and on the LSZH is 52%. No signs of abrasion are visible anymore, so this fits pretty well to the mini extent cables. Comparable to the dry tests, the HDPE cable does not show any difference, either if it's PE or a flame retardant PE. But for the LSZH, even the lubricant did not avoid the negative influence of the flame retardant duct, which means that the duct with its grooves is not fully covered by the lubricant, so this cannot be overcome. So we're already at the end of the talk here, so I want to summarize and conclude all these investigations that I've shown. So on the one hand, I can say it was possible to compare coefficient of friction with different materials in the same test setup and cable designs, especially in a very application-oriented test method. By increasing the number of tests with the same specimen, we were able to identify and emphasize effects of wear and to conclude and understand effects for long-distance blowing. The polyamide has shown improved performance in comparison to HDPE and of course also to the LSZH when we talk about dry environment and being installed there. But by the application of a lubricant, as it is normally done during blowing and installation, this difference can be overcome and the performance can be even better. A very comparable effect was also identified by using the admixed polymeric additive. And overall, we also saw that we do not only talk about cable materials, we also need to start talking about duct materials, especially when we use the flame retardant cables for the indoor ducts. So I want to thank you everyone for listening, for following up this presentation. I also got a lot of positive feedback already from IWCS, so thank you everyone for reaching out to me. I also want to thank the team because I said there were a lot of tests done, a lot of extrusion tests and testing and things. So first of all, thank you very much. And I would say I'm open for questions.
Well, thank you very much, Michael. Again, a very interesting and important presentation with great technology and information. One question that came in, I know that the polyamides and HDPEs are very tough materials mechanically, but do you have any feel for flame retardant PVC type compounds, because in different parts of the world with different requirements and applications, I'm sure we face similar issues rather than with the olefinic solutions.
Yeah, I think this is a very good question. I mean, based on my experience, it strongly depends on the amount of plasticizer that you have in your PVC. Mm-hmm. So I think this is also the reason why a lot of PVCs are rather classified by hardness. also of course by flame retardancy, but also classified by hardness. So I guess the harder the PVC is, the better would be the blowing performance. We have not tried any PVC cables here because in Europe, PVC cables are not very applied a lot. But I would say, yeah, I would say it depends on the hardness. And I guess you also would need to check a little bit on the lubricant to avoid that you create some plasticizer migration, which might be supported by a certain type of lubricant out of the PVC cable into a duct.
Yeah, that definitely makes sense. Again, I invite everyone, if you have questions, to enter those questions in the chat box at the right of your screen, and we'll certainly ask those questions to Michael. Michael, for the very lightweight micro cables, did you consider using any anti-static additive?
Actually, I think this is a very good point. That might be the static force is something that is normally not considered in a lot of the literature. I think on last year's IWCS, we had a paper out where we wanted to classify the maximum allowable push force, which mainly considers the bend radius of the cable, the coefficient of friction, but also the stiffness of the cable. On the very light cables, and I guess we're moving further towards that direction when we talk about making cables smaller and smaller. That means in the end, the best positive effect to have only pure fibers in a duct, but then actually the duct is the cable, but maybe it's not too bad. We definitely need to consider a static charge. So normally some cable compounds have antistatics on them, but rather about talking about being able to unwind them off a drum and avoid a very strong sticking. But this is definitely a good point, and to be honest, I've not considered that one in the coefficient of friction. But of course, you create a lot of static charge when you just rub plastic on plastic.
Yeah, that's true. So that is a good suggestion. Did you happen to examine the effects of a permanent lining, such as silicone, on friction?
So the maybe I don't. What is meant by permanent lining? Just like a full coverage, or?
Yeah, I would imagine you're talking about internal linings for the duct, perhaps.
Yeah. Not yet. We're doing this. We're investigating further in different ducts. So different suppliers offer different solutions to further work on coefficient of friction reduction. There are several different approaches. The ducts that I've shown here are grooved to reduce the contact area, and also to enhance the airflow underneath the cable, while others add some kind of incorporated lubricants and these things. So not yet, but we are working on that topic definitely, to further understand and also to give our customers some guidelines and recommendations how to treat our products the best way they can, so that they get the best performance.
Good. Okay, again, if you have any last minute questions, I don't see any more at this moment in time in the chat box, but any more questions? Oh, I see one. Here we go. Do you believe there is enough frictional energy to melt lower MP materials common in LSZH as compared to higher melt point high density polyethylene?
So I think I hope I understood it right. So that if something in a compound starts melting and could increase coefficient of friction?
Yeah, basically, yes. The lower melting point materials,
Yeah.
common, like the halogen-free, low smoke, zero halogen, compared to higher melt point of HDPE.
Yeah, I mean, in the standard LSZH compounds, so I would say 90% of the compounds out there are based on EVA LLDPE. And for the EVA, we talk about melting temperatures between 60 and 80 degrees centigrade. So that's true. It could be locally, it could be pretty warm by the friction. But luckily, if you install by blowing, you have a pretty strong, cold air stream that cools things down pretty much. And so what we tried to somehow simulate, because I also got the feedback that that for blowing, it heats up and it increases the friction over time. We tried this with our test method. And this was done just by repeating the tests that I've shown you again and again without any break, without any pause in between. And we have not seen an increase in coefficient of friction. But I understand that we are talking about different testing or different installation speeds in blowing. So this is something that definitely needs to be considered. But overall, yet we have not observed any significant impact due to the very cold air jet in there. And still, I would say a certain difference in between the installation temperature and the melting temperature of around 50 degrees centigrade.
Good. Do you happen to know why fresh cables exhibited a lower coefficient of friction than the original cable in some cases?
That is a very good point, and we are still doing some double check experiments on that one. The theory up to now is that we have the grooved ducts in the cable, and we just make them a bit more even. Just reduce the hard, sharp edges in the grooves by our cable, and potentially fill some of the sharp edges a little bit better. Because the difference was not as high as the friction increase on the other side. So, but this is something where we still want to double check. Up to now, we have not found any abrasion that was stuck in the grooves. So we rather think about some effects of smoothing the inside a little bit better.
Okay. Well, good. I'm seeing no further questions. We'll try and keep an eye if any last second questions will come in. But again, thank you so much, Michael, for this excellent IWCS paper presentation. I want to provide the contact points being shown now on your screen. Should you wish to contact Michael after today's event. And please know that each of these webinar series presentation events are recorded, and they'll be archived on the IWCS website normally within a week or two after today's presentation. So you can also revisit that and watch again. I also invite you to find paper 6-5 on the currently the open content library on our IWCS conference website. That is still available on demand through, I believe, middle of November sometime, November 12th or 19th. Anyway, you can watch it there. As soon as that is complete, we will we'll have these papers uploaded onto our archives as well on the website. The IWCS webinar series will conduct technical presentation webinars, as well as some sponsored company events several times each month going forward. Our next scheduled webinar event will be a technical paper That will be on Friday, November the 19th, and it will be at 10:30 a.m. Eastern USA, or 4:30 p.m. Central Europe. You gauge your time zones. Each of you will be receiving an announcement for the event. So please feel free to share our announcements with your colleagues so that they can join and register as well. Michelle or Becky, do you see any last minute questions? I'm switched over to my screen. Anything else for Michael? Excellent. Okay. All right. So before we conclude, it's important that we recognize and thank our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and their generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, thank you to these leading suppliers in our industry for your support. I also want to remind you that even though we're just now wrapping up this year's conference, we are actively and eagerly looking forward to the conference in 2022. So for over 70 years now, this is our 70th anniversary, the IWCS Cable and Connectivity Industry Forum has been the recognized leader, showcasing new technologies in the cable and connectivity products, applications, and processes. So with confidence and perseverance, our next 71st annual Cable and Connectivity Industry Forum will now take place live, and we all hope it will be live again, Monday through Thursday, October the 10th through the 13th, 2022, at the Rhode Island Convention Center in Providence, Rhode Island, USA. Please watch your inbox, your social media, and our website to learn more about the exciting information as it becomes available. You can visit IWCS.org to get more information. So again, thank you for participating today. And this concludes today's webinar event. So Michael, thank you.